Welcome to This Explainer. Today we're unpacking a truly high-stakes AI story, drawn directly from a fascinating new research paper on electricity load forecasting. Think of it as a classic David versus Goliath scenario, but in the tech world. It's a story where precise, elegant engineering takes on brute force complexity. And the battleground? A system designed to predict power demand for Panama's national interconnected system.
To really understand why this matters, we have to start with a surprisingly simple question. What happens when a power grid guesses tomorrow's demand wrong? You see, forecasting electricity demand for a place like Panama isn't just some abstract math puzzle. It is quite literally about keeping the lights on. Power grids have to perfectly balance supply and demand in real time. If you underpredict, you risk dangerous blackouts. But if you overpredict, you waste huge amounts of resources spinning up power plants you didn't actually need.
So the crucial point is that in the world of power systems, an error of just 1 to 2% translates to tens of millions of dollars in avoidable wasted costs, or in isolated systems, severe reliability risks. So yeah, every single fraction of a percent of accuracy is worth an absolute fortune.
Okay, let's dive into this. Here's our roadmap for how a uniquely engineered AI framework solved this massive real-world problem. 1. Predicting the power grid. 2. The Titan V8 framework. 3. Stopping data leakage. 4. Simple versus complex AI. And 5. The ultimate stress test.
Section 1. Predicting the power grid, the stakes of forecasting.
To grasp the stakes here, we have to look at Panama's demand curve, which is notoriously tricky. It's got this pronounced double peak shaped by the tropical climate. Before this new research came along, the benchmark reference study used a highly complex deep learning model called an LSTM network. That baseline model achieved a mean absolute percentage error, or MAPE, of 3.21%. Now, 3.21% might not sound terrible, but remember that 1 to 2% rule. That kind of error leaves millions of dollars on the table. The researchers behind Titan V8 promised they could do better, much better.
Section 2. The Titan V8 Framework. The Contenders.
And this brilliantly illustrates the researchers' approach. They designed a dual-track experiment, basically setting up an AI battle between a lightweight David and a heavyweight Goliath. On the left, track A is our David. It's a very shallow, simple neural network with just 4,289 parameters, looking at 30 carefully engineered features. Now, over on the right is track B, our Goliath. This is a deep, highly complex residual network boasting nearly 40,000 parameters and analyzing 45 different features. Track B was essentially given everything you'd intuitively think an AI needs to be smarter: more depth, more data, and way more complexity.
Section 3. Stopping data leakage, the anti-cheating mechanism.
But before we see who won that showdown, we have to look at arguably the most crucial engineering step in the entire framework: keeping the AI honest. Target leakage is essentially an AI cheating on its test by peaking at the final exam. It's exactly like a student taking a practice test with the exact same questions as the real thing. They look like an absolute genius in practice, but they completely fail in reality. If models stack together, like Titan V8 does, it's incredibly easy to accidentally feed future answers into the training data.
To completely eliminate this cheating trap, the researchers engineered a temporal out-of-fold stacking pipeline. Instead of just throwing all the data at the model at once, it slices the timeline up so the AI is constantly forced to predict the future completely blind.
Here's how that data flow actually breaks down. In step 1, the data is split into 4 chronological folds. Then in step 2, the base AI models train on the early time periods and are forced to predict only on unseen future folds. They literally never predict on data they've already seen. Finally, step 3, a master model, called the ElasticNet MetaLearner, takes only those blind, out-of-fold predictions to make its final forecast. By chaining it forward through time like this, the researchers had mathematical proof that their AI wasn't just memorizing the past, it was genuinely learning how to predict the future.
Section 4. Simple versus complex AI. The plot twist.
Now, what's really interesting about this slide is the result of the showdown. With a leak-proof testing ground established, you'd think the massive heavyweight model would crush it, right? Nope. The winner is track A. The much simpler track A defeated the complex model entirely, achieving a stunning 0.4842% error rate. Track B, despite having almost 10 times the parameters, was actually less accurate, clocking in at a 0.6177% error rate.
Let's just put that into perspective for a second. The old baseline was a 3.21% error. Track A brought that down to 0.48%. That is a staggering 6.6 times improvement over the previous benchmark. And how did the simpler model pull this off?
not by adding complexity, but by engineering smarter inputs. Track A explicitly fed the AI 24-hour and 168-hour lags. It basically told the AI, hey, look closely at what happened exactly 1 day ago and exactly 1 week ago. Because electricity demand is so heavily tied to human habits, those simple, highly correlated clues were vastly more powerful than just throwing massive neural networks at random data.
In fact, Track A didn't even just rely on one model, it used an ensemble, which you can think of like a voting committee. The master meta-learner trusted the simple neural network with the lead vote at 48%. Then, it blended in 2 different gradient boosting tree models, HISGB and XGBoost, for the remaining 52%. By letting these 3 simpler models cover each other's blind spots, the whole system achieved an incredibly accurate consensus.
Section 5. The ultimate stress test. The real world.
Okay, so creating an AI in a tightly controlled lab is one thing. Surviving the chaos of reality is entirely another. Look closely at the timeline of the dataset they used. The model stopped training in November 2018. It was validated up through August 2019. The final, pure testing window ran from September 2019 to June 2020. Do you notice anything about those specific dates? That final testing window perfectly captures March and April of 2020, the onset of the global COVID-19 pandemic. Human behavior changed literally overnight. Workplaces shut down, everyone stayed home, and grid demand dropped off an absolute cliff. The AI had never seen anything even close to this in its training data.
Let's move to and see how this builds into the final performance metrics, which show Titan V8's true strength. Even during a global pandemic that completely scrambled historical demand patterns, the model did not break. Track A's monthly error never exceeded 0.762%, not even once. It remained highly stable across all seasonal variations, holidays, and an unprecedented global lockdown, all while staying comfortably well beneath that critical 1% threshold we talked about earlier.
Which leaves us with this final, provocative thought to take away from this explainer. The researchers could have easily thrown more layers, more parameters, and more sheer computing power at this problem. I mean, Track B proves they literally tried, but Track B lost. So when building AI to solve critical, real-world problems, do you really need more complexity, or do you just need better engineering? Titan V8 proves that carefully engineered simplicity, armed with the right features and strict anti-cheating rules, can not only beat brute force complexity, but it can predict the future with astonishing accuracy, even when the world turns completely upside down. Thank you so much for joining me for this explainer. Keep learning, and I'll catch you on the next topic.